Good afternoon. My name is Chang-Hsien Tsai. My English name is Luke, so you can just call me Luke. This is my first time to a BSD conference and the first time to US. For me, every day is a new experience. The first thing I learned is I need to improve my English listening skill. Because if you guys are talking too quickly, I usually don't follow, and I will just smile. And in these 2 days, I only watch and listen and try to learn. In this hour, I will share my work with you. In my day job, I work on a company who developed ZFS new feature and improve its performance on the FreeBSD platform. In my spare time, my main interest is in security and dtrace, so I will develop some patch and send to the BSD. This is my work in my spare time. The title is Improve MemoryGuard support for UMA on FreeBSD. First, I will talk about what is the background of this work. This work is about detection kernel memory error and what are the current facility in the kernel to detect this kinds of memory error, which is about invariance, RedZone, and the MemoryGuard. And what is UMA? UMA is also called the ROM allocator in other OS. And what the support in MemoryGuard to protect this kind of memory. And what the first part is about my enhancement on MemoryGuard to support more complete UMA ROM. And the last part will be the bugs I found use this new tool. Okay. First, the memory error is about the dynamic allocation memory in the FreeBSD system. There are 3 kinds of memory error in this. The first is read before initialization, which is after you allocate a memory, you did not initialize the memory and use it. And the second one is use after free. So if you malloc a memory and use and then free this kinds of memory, and then another user use it, but the original user to write to the same memory, you will corrupt the memory which is now used by another user. Another one is read after free. If you read after you free the memory, you may read the memory which is currently used by another user. And the third kinds of memory error is memory overrun, which I divide to 2 kinds. One kind is write overrun, which is write over the range of the memory you allocate, which will corrupt the data nearby this memory. And read overrun, you will read the garbage behind this memory range. The current kernel facility, such as invariance, you can detect read before initialization and the write after free. And use the RedZone facility, you can detect write overrun. But if you use MemoryGuard, you almost can detect all 3 kinds of memory error. So MemoryGuard is a very powerful tool in detect dynamic memory error. As you know, invariance is a state of detection, such as a stir, added in the kernel to detect error condition. The part about malloc and free is added by Jeff in 2002. When you free the memory, this invariant will override the memory with 0x decode. So if you find your kernel panic in the virtual OS, at the decor, you will not use this kind of memory which is already free. Or you have some weird variable value as decor, you will know. You use the memory is free. And when you malloc again, the malloc will check the memory is with 0x decor. You will know if the value is not the same. You will know there is a write after free bug in here. And you will report the type of the let's use the memory type for debugging. Okay, the second kernel detection facility is RedZone. This is added by PJD in 2006. The facility will, when you allocate a section of memory, it will add more additional 16 bytes before and after your data. This is called RedZone. It tries to protect this range of data. The additional 16 bytes will contain the value of 42. When you free this kind of memory, you will check the additional 16 bytes of data is still 42. If the value has been changed, you will know there is a write overrun in this kind of memory. Now we will talk about the MemoryGuard. The facility is added by biennial in 2005. The facility is used by when you free memory. It will call VM protect to set this memory page as read-only. So if you free the memory, you cannot to write this section of memory again. So this can detect right after free bug. And then in 2010, MDF further improved the MemoryGuard. He used the VM map find space when you malloc memory to find available kernel virtual address, and then you use kmem back to allocate the physical address. Also, he added a function to detect read and write overrun. The function is add one more additional page before and after your memory. But it allocate the virtual address, but not back the physical address. So if you access the before and after area, it will result in a page 4 panic. You will know you have the memory overrun error. And you know the facility is depend on the page system. So if your native page size is 4K and you allocate 1K data, you will try to alignment this 1K near the end of the 4K page. So if you memory overrun, it will easily run into the next page. In this way, you will detect small size memory overrun. Okay. When you free the memory, it will call VM map deleter to free the physical address. So the old memory will not be accessed again. Otherwise, you will result in a page 4 panic. In 2011, the MemGuard tried to support the UMA system. And the list work is about this. So what is UMA? UMA is called Universal memory allocator, which is also called zone allocator in other OS. First, you need to use this function UMAG to create a new zone. So you give it name and the object size. And the BSD version of UMA is very flexible. You have 4 kinds of constructor, destructor, and the initializer, finalizer to initialize and destruct this kind of object. And you can alignment and the additional flag to customize this zone. So when you create this zone, you can allocate the same object from UMA and free the object to UMA. This will have efficient use of object in the UMA cache. So normally, when you call UMAG allocate, you will ask the zone to give you a range, a object, and the UMA will call VM system to give you some backend page. So normally, you will call Init before VM system return the memory to the UMA system, and then UMA call constructor before it return to the UMAG allocate. After user use the memory, it call UMAG free to return the memory to UMA. So normally, you will call once UMA init, and then use by call constructor, and free call destructor, and then call constructor use again. So you will very efficiently use this kind of object cache. And after, if your VM system is in low memory condition, you will call UMA zone to drain its use the memory. So you will return to the VM system and call fini to do the destructor on this memory. What I say about mainlock is also allocated in the UMA, which doesn't have the constructor, destructor, initializer, and the finalizer. So this is a normal UMA. For MemoryGuard to support the UMA system, the main job is to support these 4 kinds of function pointer to constructor and initialize the object in UMA system. So MemoryGuard, when you use MemoryGuard to protect this ROM, you will allocate from the memory and call init and call constructor and return to a user. After user call UMA free, you will directly call destructor and fini, return to the VM system. So if you MemoryGuard, you lose the cache efficiency, but it stimulates all the functionality of this UMA function. So next, I will talk about the enhancement I work on MemoryGuard. The first thing I found in the UMA is the current implementation of MemoryGuard is called zone init and zone finish. When you allocate and free the memory, but the zone init and the zone finish are not the UMA init and the finish function, because under the hood there is a CAC system, which is the backend for the zone. So the correctly initializer should be CAC init, and the correct finalizer should be CAC finalize. So if you don't use these 2 functions, you will neglect the initialization of the object, which will cause many problems. The second problem I encounter in two is the UMA zone per CPU. This is a special zone for allocate per CPU counter. But the current implementation, MemoryGuard will only allocate the allocate size of this counter. But actually, it should allocate the size plus size of structure per CPU times the number of CPU. If you not correct the correct size, you will run into the panic. You are happy you find the bug, which is I think so. But actually, when I to read more into the code, I know this is not really bug. This is because for this kind of zone, you should calculate the size with additional size about the per CPU structure. The third kind of problem I come into the MemoryGuard is when you use the reallocate with the M wait OK option. It means you want to reallocate the memory, but you want to wait the allocate the memory successful. But the problem is when you relocate the address, which is already allocated by MemoryGuard, you will first call MemoryGuard allocate to allocate another section of memory which is protected by MemoryGuard, and then copy the memory into the new memory and return it. But if you find the MemoryGuard allocation fail, you will return null. But it will surprise the user of relocate because he specified the M with OK. It will not expect the pointer return will be null. So you will run into any kind of problem, always panic. So the correct solution is when you call if MemoryGuard allocate in this situation, and you cannot allocate the KVA address in the MemoryGuard, you should fall back to the normal malloc and return the normal malloc to the user. The third problem I come into is the lock already init assert. Because the UMA init function usually used to init the lock, so the object only need to allocate and init the lock once, and use the lock many times. But if you allocate memory happen to have initialize lock, you will run into this kind of assert. There are two solutions to this kind of problem. The first kind of solution is in this initial function, you should B0 the memory allocate from the VM system before you call the lock init. Okay. The second solution, which is I might recommend, is use the new flag, LO new, in the lock init. If you use this flag, the FreeBSD will know you are allocate a new lock and don't check this kind of assert. So how to use this LO flag? If you are mutex init, a new mutex, you add the option mutex new. And if you use the remote new lock, you will add the remote new option, etc. So even with this kind of work, there are still some wrong we cannot support. The first wrong we cannot support is UMA wrong reference count. This is kind of wrong used in network stack, I think, I run into. Because this kind of wrong, you save the reference count in the VM page structure. There's a union structure in the VM page, which happen to also used by the MemoryGuard. MemoryGuard used the same union. He saved the allocation size and request size. And when it's free, you will use this value to know how much memory you allocate and how much memory the original user allocate. So these two functions are conflict. So in the current situation, this kind of zone cannot be protected by MemoryGuard. Another two zone is UMAG flag bucket and UMAG zone free, which is used in the bucket system and the VM system. If you protect these two kinds of zones in MemoryGuard, you will run into the recursive location and easily to run to the recursive lock assertion, panic. So in current situation, I don't know how to bypass these two. So current situation, if the allocation type is these three kinds of zone, I will bypass MemoryGuard and use normal UMA functionality. Now I will share the experience. I use the improvement version of MemoryGuard to find some new bug in the FreeBSD system. The first one is in the pipe deconstructor. When you call the pipe close, it will free the D pipe memory. And then in the next line, you will see it use the D pipe field, P pipe state, and do something. So this is one kind of use as the free bug in a FreeBSD system. This exists a very long time, I think many years. So I reported the bug, and this is already correct in the current FreeBSD system. And another is a tricky bug about in the Galley module. This is the Juon encryption module. There is two functions. One is Galley also run, and another is Galley crypto run. And when you call the crypto dispatch of the CRP, if all the file is also served in a GVFS down, you will free the BP. So there is a rest condition here. If it already free, and then you use the if bio error and assign the BP bio error, there is used as a free bug here. This also report and fix. And there are two used before initialization bug here. This is used in the straight ROM. Before this implementation, this will not be detected because the straight init function is the straight zone initiator, which is not called in the current MemoryGuard. Okay. So when you call this function, you will see it is not initialize the TD SDL field. So when you in the SDL TD init function, there is the use of before initialization. If you use MemoryGuard, you will easily to find this kind of bug, because in normal situation, the value is usually 0, so you will know nothing happen. But the VM system doesn't guarantee the memory return the value is all 0. So if you got a field that is not 0, you will think the field is already allocated. So you will not allocate the memory for TD SDL field. So you will use a dangling point here. So this bug is also reported and fixed. The third bug, the fourth bug which I found recently. This is the code in the GFS system, which is there is a function called km catch allocate, which is the enormous type of UMA. But the enormous UMA is not flexible as FreeBSD. The enormous UMA only have initializer and finalizer. Well, it called initial constructor and destructor, but it is the counterpart in BSD is initializer and finalizer. And when you allocate a new handle, which is SA, and then call DMU buffer init user, pass the SAD buffer, and then in the DMU buffer init user, he check the EV function is null, but this field doesn't be initialized. So this is the use before initialize bug. This bug is also reported and fixed. Conclusion is MemoryGuard is very effective on detection of this kind of dynamic memory error. This is good use for developing and testing. In current situation, I only run MemoryGuard and turn on all the ROM protection, and I try to compile kernel and run the tool regression, pass all the tests in the tool regression, and find these two kinds of bugs. As you see, I don't find any memory overrun error because it seems our test case don't produce any weird error for test case. So in the next stage, I will try to run the fuzzer or write my own fuzzer to produce abnormal value and try to find some memory overrun error in the BSD system. So this is my talk today. So any question?
Hey, so you said you're running it through, so for dynamic analysis, obviously you need to actually execute your stuff to catch the bugs. You said you're just compiling kernels and running it through QA or whatever it's called, the built-in regress stuff. What would it take to have this be on by default as not like a panic, but as some kind of, hey, go look here, so you could roll it out into, I guess not production, but some place that has enough wide workload? Is it something you could have be, what would it take to roll this out where you would have more testing?
If I run into panic, I will try to run the test case again and try to find out what zone I allocate, and or find more information in the DDB or KGDB. I know what you want because there is one feature which I can add to the system. For example, in the RedZone, if you find the memory is be cropped, you will print a backtrace of where the memory is allocated. This may be helpful for debugging. Okay, and you say you want to deploy this situation in the production. You don't want to panic. In current implementation, you have no way because it depends on the virtual memory system, and the patch 4 will call to panic. So I have no way to turn it to in the result or printf like debug message.
So right now it's just going to when you detect some corruption, you're just always panicking?
Yes.
Could you have it add a line to the D message or something with the, hey, go look here, and be able to still have an operational system? Just to try to get it into more places. I don't know. Yeah.
Oh,
have you looked at trying to get it into on by default status?
No, I haven't tried.
Okay.
Okay. Because I always use the QA and testing situation.
Thanks.
Thanks.
A sort of related question. I was interested to know what kind of overhead is associated with turning the feature on. How much more memory does it end up taking, and how much more CPU does it end up taking?
I have no idea how much overhead it will cost, but the memory is almost the same. Because in the new implementation, if you don't use the memory, you will free the physical memory, and it will not cost any memory. But the performance overhead, I think there's little performance overhead. Because I don't deploy the system in production, and I use develop this kind of system in my own in my VM system, so I don't notice how slow it will cost.
On your first slide for MemoryGuard, you said that right. When free VM map protects sets read only, why not set it not read either? In other words, something is free, you don't want anyone reading that page.
Yes.
So you made it read only, but why not make it no access at all?
Yes. In the original implementation.
I'm sorry, yes, their original implementation.
Yes.
Why did they do that, do you know?
Because you want to use the VM page protection, so you use the VM page protect. It can only set read write execute, so it's selected to set read only to protect this page.
Thank you.
Okay. Any question?
Thank you, Luke. I appreciate it. Appreciate it.